A strip of grey dust is sitting on the seal of an airlock. It does not look dramatic. It looks like something a gloved hand could brush away in a few seconds. The hatch is small, and the room behind it is small enough to feel manageable. That is part of the moon's trick. We know its face. We know its distance. Humans have already stood there and come home again. The surface can feel almost familiar before the harder truth catches up. But a landing and a base are not the same machine. A landing mission can leave before the little problems become the whole story. A base has to close this hatch again tomorrow, and the day after that. It has to keep pressure inside, dust outside, air moving, water cycling, batteries charged, electronics warm, and people alive while the outside never becomes forgiving. That is the question hiding inside this quiet seal. What actually stops us from building a dependable moon base? By the end of tonight, you will understand why reaching the moon again is not the same thing as creating a place that can keep working there after the landing has already been forgotten. If you enjoy exploring questions like this with me, subscribing to the channel helps others find them too. Sharing the video helps even more. Let's begin. Apollo is the reason this question refuses to go away. If no one had ever landed on the moon, a permanent base could remain a distant ambition. We would say the place is too far, too hostile, too expensive, and the discussion might end there. Apollo removes that escape. Humans did go. They worked there. They collected samples, deployed instruments, drove rovers on the later missions, and returned with proof that the lunar surface is not beyond human reach. So why did that achievement not become the beginning of staying? Look closely at what Apollo actually was. It was a sortie system with a built-in ending. The crew arrived with a return path already embedded in the architecture. Surface time lived inside a clock, and the clock mattered as much as the science did. Consumables were finite. Fatigue mattered. The health of the spacecraft mattered. The mission only had to remain coherent long enough for the astronauts to complete a bounded set of tasks and climb back into the vehicle that would take them home. That is a very different kind of success from operating a base. Apollo hardware only had to win for the duration of the mission. Dust could be severe without yet becoming a permanent cleaning economy. A seal could suffer wear without forcing anyone to think about the same interface after hundreds of cycles. Rover tires, suit joints, batteries, sample tools, and cabin filters all lived inside a short operational story. If they held together long enough for the crew to finish the sortie, the system had done what it was built to do. The Apollo Lunar Surface Journal and the wider NASA historical record are useful for exactly this reason. They show how real and how bounded the work was. EVA time was precious, crew energy was limited, every added task had to live inside tightly managed margins. Apollo proved that lunar surface operations are possible, but it did not try to make the moon ordinary. It tried to make a visit succeed. You can feel that bounded logic even in the shape of the missions. The cabin was not trying to become a place where people could settle into weeks of routine repair and replenishment. It was trying to remain viable long enough for a sequence of surface work and a return. The ascent stage did not wait on the surface as an optional backup plan. It was the ending built into the architecture from the start. That matters because a base loses the comfort of that built-in ending. The more permanent the site becomes, the less it can treat departure as the clean answer to growing wear. Even the rover lessons point in the same direction. On the later Apollo missions, the rover widened the crew's reach and made the surface feel larger, richer, and more workable. But it also widened the zone in which dust, tire wear, navigation, and tool handling had to stay inside mission margins. That was acceptable because the rover did not have to become a municipal vehicle. It had to carry a crew through one expedition and then stop being anyone's problem. A base asks a different question. Instead of asking whether astronauts can finish a mission before the clock runs out, it asks whether a local human-made system can keep itself healthy after the mission clock stops being the main organizer. Pressure has to hold tomorrow as well as today. A filter change has to fit into maintenance cycles instead of a mission finale. A hatch, a rover, or a pump cannot be allowed to age out of confidence just because the crew is tired and the interesting work already happened. That is why days on the surface are not yet an operating regime. An operating regime begins when the same interface must still be trustworthy next month. A dusty return through the airlock is no longer memorable then. It is simply one more cycle that has to be cleaned, inspected, and logged. It begins when the crew cannot rely on departure as the elegant answer to accumulating wear. The key variable is no longer arrival, it is repeatability. A base also inherits obligations Apollo did not need to carry. It has to think about where spare parts are stored, where dirty tools are cleaned, where a damaged suit can be isolated, and where a crew shelters if another system is already unstable. Those are not side details. They are the difference between a mission vehicle with a departure date and a local operating system trying to remain calm after the big moment is over. Apollo also hid one of the moon's most misleading features, nearness. The moon is close by the standards of spaceflight. That is true. A few days sounds emotionally local compared with Mars, but local in the practical sense means something else. If a pressure boundary begins to fail, if the oxygen loop behaves badly, if a power distribution line goes down, or if the rover needed for inspection comes back damaged, Earth is not stepping into the event in the next hour. Diagnosis starts on site. Isolation starts on site. Improvisation starts on site. That changes what resilience means. A short expedition can survive by leaving before too many invisible debts come due. A base cannot. It has to store parts, tools, procedures, and margin, because the surface itself never becomes generous. Apollo did not need to answer what happens after the 50th dusty hatch cycle, or whether the same worn interface should be patched, replaced, or retired from routine use. It did not need a local workshop culture because it was not trying to become one. It also did not need to solve the psychology of long trust. During a short mission, crews can tolerate equipment that feels temporary because temporary is exactly what the mission is. A base asks for something calmer. The crew has to sleep beside systems they expect to need next week, not simply survive beside systems they expect to leave behind soon. That changes what counts as acceptable uncertainty. A questionable seal or a noisy pump is no longer a footnote in a heroic timeline. It becomes part of the emotional weather of daily life. This is also why a bigger landing is not yet the same as the first true base step. A larger lander, a longer stay, or a more capable rover can extend the sortie model. Those are meaningful advances, but they still do not solve the habitation problem unless the surface system can continue operating after the exciting phase is over. The real moon base question begins at the moment when departure stops being the main safety strategy. Seen that way, Apollo was not a failed base. It was an extraordinary proof of visitability. That proof is encouraging because it tells us humans really can work on the moon. It is dangerous because it tempts us to treat staying there as a scaled-up version of something already solved. What Apollo solved was access. What it left behind was continuity. Near is not the same as safe. Near is not the same as repairable. And near is not the same as routine. The moon is close enough to keep inviting us back, but a permanent foothold will only begin when the hardware on the surface can keep people alive after landing has already become yesterday's achievement. Once you ask for that kind of dependability, the surface starts to look different. From inside a habitat, the wall might look ordinary. There may be a handrail, a work surface, a light, maybe a display showing steady numbers. For a few seconds, the room could resemble any other compact technical space humans have learnt to trust. Then the moon forces the correction. That wall is not separating one room from another. It is separating a manufactured atmosphere from vacuum. That is why a lunar base is a pressure vessel before it is a home. On Earth, a room inherits a planet. Air already exists. Pressure already exists. Heat still behaves inside a larger environment. If a panel ages or a door sticks, The room may become inconvenient, but the background fact of living is not usually being created by the room itself. On the Moon, the room is doing that creation. It is holding the breathable world in place. Seen that way, ordinary details stop being ordinary. A hatch seal is no longer trim around a doorway. It is a maintained edge in the pressure boundary. A cable passing through a wall is not a minor convenience. It is a place where the barrier has been interrupted and therefore has to be designed, inspected, and trusted. A valve, a window, a suit interface, or a repair patch carries the same truth. The wall does not simply surround life, it is one of the main pieces of life support hardware. This is one reason the Moon never becomes mentally normal in the way a polar station can. Antarctica is harsh. A submarine compartment is confined. Yet both still exist inside Earth. Outside may be cold, wet, thin, or dangerous, but it remains a human environment at some scale. The Moon offers no such outside. A crew member stepping beyond the boundary is entering vacuum. The act is always artificial and always mediated by machinery. That fact pushes straight into the base's internal systems. Breathing is not background. It is an engineered loop that has to keep oxygen where it belongs and carbon dioxide from rising where it should not. Temperature is not something weather will quietly help with. It is something the base has to manage through active thermal hardware. Water is not a pipe connected to a city utility. It is a trapped substance inside tanks, pumps, filters, and recovery equipment. Waste does not disappear into a wider world that can absorb it. The system has to decide where it goes next. Fire belongs in this same category of forced awareness. On Earth, smoke can often be escaped by moving into a much larger atmosphere. On the Moon, smoke stays inside the world you made. A scorched cable, an overheated battery enclosure, or a material that begins releasing something toxic does not merely damage hardware, it alters the air the crew is breathing and the pathways through which the crew is trying to respond. The habitat has to be arranged with that possibility in mind from the beginning. The International Space Station is a useful bridge because it proves people can live for long periods inside an artificial environment, but the station still leans on Earth in ways a lunar base cannot. It has mature resupply patterns, deep ground support, and an exterior that does not coat every return path with abrasive regolith. A moon base inherits the closed-loop discipline of orbital life, and then adds a harsher threshold every time someone goes outside. That threshold deserves more attention than it usually gets. Suppose a pump in the water recovery system begins to behave badly. On Earth, that is already an annoying maintenance event. On the Moon, the first minutes are more intimate. Someone sees the pressure trend drift. Someone hears the changed sound. The crew has to ask whether the problem can be isolated, whether the backup path is ready, how much margin remains, whether the repair will spend a critical spare, and what other work now has to stop. One local symptom immediately begins pulling on several parts of base life. That is what it means to say every failure starts local. It does not mean every failure becomes fatal. It means the first responder is the crew already inside the system. The first technician is local. The first person deciding whether a compartment is isolated, whether a repair waits until morning, or whether a rover sortie is cancelled is local. The Moon strips away the illusion that the outside world can absorb mistakes for us. It also strips away casualness. Familiarity may grow, better design may reduce burden, procedures may become smoother, but the outside never relaxes into a forgiving environment. There is no ambient pressure to soften a minor leak, no rain to rinse dust from exposed hardware, no nearby industrial district full of replacement options. The base has to carry its own resilience inside the shape of its rooms. That changes the emotional meaning of maintenance. On Earth, maintenance often feels like the thing delaying real work. On the Moon, maintenance is part of the real work because it is what keeps the local world intact. Tightening a fitting, checking a sensor drift, or cleaning a threshold is not a distraction from the mission. It is the behavior that allows the mission to still exist tomorrow. That is why layout becomes survival geometry rather than interior design. Where should dirty traffic enter? which compartment can serve as the safest shelter, which systems should be isolated from one another, and which must remain physically close so repairs can happen fast. Those are not style questions. They are questions about whether the human-made world inside the hull can stay organized against the world outside it. Even the airlock routine becomes a kind of architecture. If suits return dusty, where does the dust stop? Which tools can remain near the threshold, and which must be carried deeper inside? How much of the crew's day is spent preserving the line between a dirty edge and a cleaner interior? These are practical habits, but they are also part of the shape of the base. That shaping effect reaches into ordinary movement as well. If one corridor is always the route back from outside work, then that corridor becomes a pressure point in the life of the base. It may need more cleaning. It may need surfaces that are easier to inspect. It may become the place where people pause before carrying tools farther inward. A lunar outpost is small enough that habits become architecture quickly. The path people walk begins teaching the base where its burden truly lives. That legibility matters. A base becomes easier to trust when the crew can tell, almost at a glance, whether a threshold is getting cleaner or dirtier, whether a return route is spreading contamination farther than expected, and whether one part of the habitat is quietly becoming the place where too many burdens accumulate. The clearest place to see all of this is not a giant moon panorama. It is a threshold that has to open and close again. That is where inside meets vacuum, where equipment leaves clean and returns carrying the surface with it, and where the base learns over and over that the outside never becomes routine, which is exactly why the next enemy arrives as something small enough to cling to a seal. Picture one grain of lunar dust, not a poetic cloud, not a cinematic plume. One grain. On Earth, many grains spend their lives being softened. Water moves over them, wind shifts them, chemistry changes them, edges get worn down. Beach sand is not gentle because sand is kind. It is gentle because Earth has been working on it for a long time. The moon does not do that kind of smoothing. Its regolith is shaped by impacts. Particles are broken, crushed, and left in an environment without rain, rivers, or ordinary weathering to round them off the same way. The result is not magical poison. It is something more mechanically irritating and more useful to think about. Sharp, abrasive, clingy particulate material that keeps showing up exactly where a base wishes it would not. This is why lunar dust is a systems problem. The Apollo record makes that plain long before modern engineering papers do. Crews complained about dust for practical reasons. It clung to suits, darkened surfaces, got into equipment, and followed astronauts back toward the cabin. It became part of the texture of lunar work, and that was during short missions. If Apollo is the warning, a base is the scaling event. What is nuisance on a few sorties becomes maintenance debt over hundreds of cycles. Dust can scratch visors, abrade suit joints, foul bearings, contaminate seals, load filters, and settle onto radiators or optical surfaces. The point is not that any single grain is apocalyptic. The point is that the base keeps giving those grains more chances to matter. That change in timescale is the real story. Imagine an airlock seal that must remain trustworthy not for one return to cabin pressure, but for years of use. The base can brush it, vacuum it, cover it, inspect it, and design procedures around it. Good engineering helps. But every protection layer creates more routines, more equipment, more cleaning burden, and more parts that can wear out themselves. Dust is not an obstacle because it is dramatic. Dust is an obstacle because it is ordinary and persistent. It arrives on boots and rides on suit fabric. It settles into corners, hides inside hinges, and gets moved by operations that have to happen anyway. Every EVA is also a contamination event. Every rover excursion is also a transport event for abrasive particles. Every landing nearby risks mobilizing more of the surface into places it does not belong. That means dust control cannot be treated as cleanup that happens later. It has to be built into architecture. This is why so much lunar engineering attention returns to airlocks, suit ports, covers, brushes, vacuum paths, isolation zones, and traffic rules. The goal is not to make dust vanish. The goal is to keep dirty operations from constantly poisoning cleaner ones. A base that treats every threshold the same way will slowly spread the surface into its own lungs, seals, and workspaces. There is also a measurement problem here. Dust control is not only a matter of clever hardware, it depends on noticing where contamination is accumulating, how fast filters are loading, whether seals are wearing more quickly than expected, and which routes through the base are carrying the most trouble. In other words, the Moon forces even housekeeping into the domain of data and maintenance culture. And dust becomes worse when the settlement grows. More EVAs mean more returns through airlocks. More rovers mean more surface contact. More landings mean more disturbed regolith. A base that becomes more active also becomes more efficient at delivering lunar material into the exact places where precision and cleanliness matter most. How dirty is the first airlock zone allowed to become? Do suits stay outside the main pressure volume? Are there suit ports? How often do seals get inspected and replaced? What kinds of covers protect exposed mechanisms? How much filter capacity is carried? How much time gets spent cleaning instead of doing science? How many spare brushes, wipes, gaskets, and sealing elements does a base quietly need because dust is always making another attempt at entry? Once you ask those questions, the problem stops looking like dirt. It starts looking like friction inside every layer of life support. Dust also reveals something important about lunar engineering culture. A moon base cannot depend on heroic tolerance. It cannot assume that crews will simply endure nuisance until it becomes normal. The system has to be designed to make the nuisance less destructive. That requires measurement, hardware choices, traffic rules, storage discipline, inspection schedules, and eventually surface infrastructure meant to keep the base from constantly dirtying itself. Even a rover wheel becomes part of this story. A rover is not just a vehicle. It is a contact surface between the base and the terrain. Wheels throw material. They bring material back. They wear under abrasive conditions. They carry dust into maintenance bays and staging zones. If a base expands, surface mobility expands with it. That means the dust problem scales with usefulness. The more active the settlement becomes, the more actively it contaminates its own interfaces, unless it has been built to resist that. There is a temptation to think of all this as a matter of house cleaning in a strange place. It is more serious than that. For a lunar base, contamination control becomes a form of reliability engineering. The base is always trying to preserve trustworthy boundaries. Dust is always trying to make those boundaries harder to trust. That is why the opening image of a gloved hand cleaning an airlock edge matters so much. It is not a decorative gesture, it is a picture of the larger truth. The moon keeps placing its own material between the human system and the surfaces that system most needs to work cleanly. Apollo already hinted at that burden. Crews could brush dust from suits, complain about grit in mechanisms, and still know the mission would end before the cleaning problem had to become permanent policy. A base cannot end the story there. It needs routines for where dusty gear goes, which surfaces are sacrificial, how filters are protected, whether suit interfaces stay outside or come in, and how much crew time the whole cycle consumes after hundreds of repetitions instead of a few famous EVAs. Dust also follows motion. A rover does not only move people and tools across the site, it enlarges the dirty perimeter of the base. Wheels throw material, staging areas accumulate contamination. The path back to the habitat becomes a path along which the surface keeps trying to ride inward. That is why pads, routes, brush stations, covers, and cleaning procedures all belong in the dust story. The moon is not merely placing dirt on equipment, it is shaping the traffic pattern of survival. Dust is one part of the larger pressure the moon puts on the base. Because once you try to harden the base against contamination, another question rises behind it. How much shelter can you physically carry? If dust attacks the edges of a moon base, radiation attacks the idea that a thin shelter is enough. The most useful starting point is to separate two problems that often get collapsed into one word. One is chronic background exposure from galactic cosmic rays, high-energy particles that keep arriving over long periods and are difficult to block completely. The other is the more episodic danger of solar particle events, where the timing and intensity can change what the crew needs to do quickly. Those are different operational burdens. A base does not answer them with a slogan like "Shield better." It answers them with layout, mass, timing, and procedure. Where is the protected space? How far is it from the work area? What remains powered there? How much life support can it sustain if people have to stay inside it for an extended period? What do crews do if they are outside when conditions change? What happens to rovers, tasks, and exposed equipment while sheltering takes priority? Radiation is not just a wall thickness problem, it is a base behavior problem. The moon lacks what Earth quietly provides: a thick atmosphere and a global magnetic field that together reduce the radiation burden on the surface where humans live. On the moon, that absent protection has to be replaced by engineering and operations. Even if the base is small, the planning burden is large because the outside environment does not stop being active simply because humans have arrived. This is one reason a spacesuit cannot be treated as the answer. A spacesuit is a temporary working interface. It is not a permanent radiation strategy. The same is true of thin habitat walls. They may be enough to hold pressure. They are not automatically enough to create the kind of long-duration shelter a base needs for repeated occupation with acceptable risk. So the conversation turns toward mass. Mass means material placed between people and the environment. It can mean specially chosen structural materials. It can mean water in some locations. It can mean dedicated shelter geometry. It can mean regolith piled over parts of the habitat. The details matter, but the broader point matters more. Protection has weight, and weight has consequences. Every kilogram that helps shield a base has to be launched, landed, assembled, or moved locally. That sentence sounds abstract until you imagine the alternative. A beautifully arranged habitat with thin walls and elegant systems might be enough for short missions. The moment you ask it to become a place where crews remain through repeated exposure cycles, the need for better shelter begins to push on everything else. More mass means more transport. More local shielding means more excavation, hauling, placement, verification, and maintenance. This is where regolith enters the story in a dangerous way. It is easy to say, use local dirt for shielding. That is directionally sensible. It is also incomplete. Regolith is useful because it is local mass. But local mass is only helpful after it has been turned into protection by machinery and work. It has to be moved from where it is into where the shelter needs it. That demands excavation tools, hauling methods, dust-tolerant components, power, crew supervision, or robotic autonomy, and confidence that the placement is actually doing the job intended. Nothing about that is free. The moon does not hand you shielding in the shape you need. It hands you material that can become shielding if another layer of engineering succeeds first. That has an important consequence for architecture. The safest place in a base may not be the easiest place to build, the lightest place to launch, or the simplest place to access. Storm shelter logic can affect internal layout. Buried sections may complicate repair access. Exposed radiators and cables may need to remain outside even when protected living volumes move inward. A base begins to look less like a neat cluster of modules and more like a negotiation between survivable spaces and serviceable spaces. There is also a psychological shift here. When people say the moon is close, they often imagine that closeness has reduced danger. Radiation reminds us that astronomical closeness is not the same as environmental kindness. The moon may be nearby on a cosmic map, but at the surface level it still asks for the kinds of protective decisions associated with a place that never becomes safe by default. A lunar base therefore needs more than confidence in launch capability. It needs a credible answer to the question of where the crew goes when the outside conditions become less forgiving than usual. And a credible answer is not a line in a concept brochure. It is measured in routes, minutes, walls, materials, and the ability to keep critical systems running while the crew is under shelter. Over months and years, that pressure changes the rhythm of life, even when no emergency is happening. Exposure budgets shape where people work, how long they stay outside, how often inspection routes are worth repeating, and which tasks are pushed toward robotics instead of human EVA time. Radiation planning is therefore part of schedule design as much as shelter design. The base cannot wait for a solar event to start caring about dose. A refuge also has to be more than a thick corner of the habitat. It has to be stocked, powered, ventilated, and reachable from wherever the crew is likely to be when the warning comes. If extra mass is placed around the refuge, that mass has to be moved and kept where it helps. If a rover returns late, the route from the airlock to shelter still has to make sense. The clock matters because the system has to become practical before it becomes reassuring. Radiation also changes how the crew reads time outdoors. A long repair on Earth can often be extended because the team is making progress. On the Moon, progress is only one part of the calculation. Dose accumulation and shelter distance are ticking in the background. A stubborn job on an exterior panel or rover may have to stop, not because the crew lacks skill, but because the site has reached the point where another half hour outside costs too much margin. The environment keeps interrupting the human instinct to simply stay and finish. That interruption matters for planning long before any alarm ever sounds. Tasks are grouped differently. Exterior work windows are chosen differently. A repair that would be mildly inconvenient at one location on the base may become unattractive at another simply because the shelter path is longer or the geometry is worse. Radiation is not only a danger to endure, it becomes one of the quiet forces shaping where the whole settlement wants to place its most important hardware. It also changes the meaning of success outdoors. Finishing the job is not enough if the crew has spent too much of its margin doing it. A good plan leaves enough safety in reserve that the next problem still looks manageable when the first one is finally done. This matters even more once we choose the place many real plans keep returning to. The lunar South Pole sounds promising because it may offer both useful light and useful water. But promising is not the same as gentle. Look at a map of the lunar South Pole and it is easy to understand the attraction. Some high areas can receive long stretches of low-angle sunlight. Nearby permanently shadowed regions may preserve water ice and other volatiles because they remain extraordinarily cold. If you are trying to imagine a first serious base, that combination feels almost too convenient. Light for power, shadow for resources, a place where the moon seems to offer a workable bargain. Then the geometry begins to bite. The South Pole is not a flat, welcoming industrial park. It is a landscape of crater rims, harsh shadows, low sun angles, difficult lines of sight, awkward traverses, and cold traps that preserve what makes them valuable by also making them hard places to operate. That is why a polar site is a trade-off, not a solution. The light is real, but it is not simple. Long periods of illumination are not the same as uninterrupted, effortless power. Low-angle sunlight creates long shadows. It complicates visibility. It can produce tricky thermal patterns. It turns site placement into a routing problem for cables, batteries, radiators, communications equipment, and traverse paths. What looks bright on a concept rendering may be mechanically awkward in actual terrain. The shadow is real too. Permanently shadowed regions matter because cold can preserve volatiles. That is why those regions attract attention. But the same cold darkness turns resource access into an engineering burden. If you want machinery working inside or near those areas, you are asking it to handle extreme cold, limited direct solar energy, rough surfaces, difficult communications geometry, and the same dust and maintenance problems that already haunt the rest of the base. This is where the South Pole stops looking magical. Its promise comes attached to work. Suppose you place a habitat near a ridge with favorable illumination. That choice may help with surface power. It may also put your prospective resource zones farther away, across terrain that complicates hauling and inspection. Suppose instead you bias toward easier resource access. You may inherit worse lighting geometry, harsher cold exposure, or more difficult power routing. The Moon keeps insisting that every advantage arrives connected to another burden. That pattern is not a design flaw in one agency plan. It is part of the place itself. Even the phrase peak of eternal light, often used carefully but remembered lazily, can mislead. The problem is not that the idea is false in spirit. The problem is that listeners can hear it as permanent, easy brightness. Polar illumination is more nuanced than that. Ridges, rim segments, seasonal geometry, low sun angles, and local topography all shape what the base can count on. Reliability comes from detailed site understanding, storage, redundancy, and routing choices, not from poetic labels. The same is true of lunar water. If a map suggests hydrogen or ice signatures nearby, that is encouraging. It is not the same as seeing clean blocks of usable ice waiting at a convenient depth next to the habitat. Evidence of resources guides planning. It does not erase the industrial steps between evidence and dependable supply. The polar environment therefore concentrates the entire moon base problem into one landscape. Light is promising but hard to distribute. Shadow may hold value but resists easy work. Traverses matter, communications matter, temperature matters, equipment placement matters. One crater rim can change the operational logic of everything around it. Navigation becomes part of the engineering burden too. Low sun angles can flatten terrain cues and make surface travel harder to read. Long shadows can hide changes in slope, wheel hazards, and the edges of useful routes. That affects rovers, crew walking plans, cargo movement, and the confidence with which equipment can be sent out and brought back. A site can be scientifically attractive and still be logistically awkward in daily use. Communications add another layer. A ridge that helps one system may block or complicate another. Relay strategies, mast placement, line of sight planning, and the routing of control signals to robots or extraction equipment can all become site design problems rather than afterthoughts. The pole is not only a map point, it is a three-dimensional operational puzzle. Thermal planning refuses to stay simple there as well. A place near long illumination may ease one part of the power problem while exposing hardware to repeated glare and uneven heating. A place near permanent shadow may help resource access while punishing machinery with cold that changes materials behavior, battery confidence, and maintenance difficulty. The base is always being pulled between favorable traits that do not naturally sit in the same spot. That means early site choice is less like choosing a destination and more like choosing which compromises the whole architecture is prepared to live with for years. Where will the safest shelter sit? Where can landing traffic be kept away from vulnerable systems? How far is acceptable between habitat and resource zone if every kilometer adds communication delays, rover wear, and another chance for something to break in low light? Those are not abstract planning notes. They are the bones of the future outpost. This is why the pole remains compelling without ever becoming easy. It is promising enough that serious programs keep coming back to it, yet stubborn enough that every promise has to be converted into hardware, routes, procedures, and margins before the promise becomes useful. This is precisely why the South Pole keeps coming back in serious discussions. Not because it makes the problem disappear, but because it makes the trade-offs worth studying. A place without useful light and without useful volatile prospects would be easier to dismiss. The South Pole remains compelling because it might support a base better than other sites, while still refusing to become easy. That refusal matters. A moon base cannot be built on the assumption that a chosen site has solved the largest constraints. It has to be built on the recognition that the chosen site has only changed the pattern of those constraints. That choice also changes how the crew feels about distance. A route that looks short on a map may feel long once it crosses from a relatively well-lit ridge into terrain where communications are thinner, temperatures are stranger, and a stuck wheel would matter much more. The South Pole does not merely offer opportunity in separate pockets, it asks the base to keep moving between pockets without losing confidence on the way. That is why site choice is really a choice about future routine. The best location is not simply the point with the nicest balance on paper, it is the point whose daily demands the base can keep meeting without surprise. That is visible even in the way people and machines would move around the site. Low sun angles can make terrain features look flatter than they are, then throw long shadows that hide hazards a short distance away. A ridge that seems favorable for power can become awkward for line-of-sight communications or routine access. A short route on a map may become a longer operational route once lighting, slope and return safety are accounted for. The pole also splits work into different worlds. Habitats and power hardware may prefer better light and more moderate temperatures. Prospecting and extraction may pull activity toward darker, colder terrain where the valuable volatiles are more likely to persist. That means cables, rovers, robotics, inspection plans, and emergency assumptions have to bridge the gap. The site does not give one easy answer. It forces the base to connect unlike environments into one operating system, and nearly all of them flow through the same dependency: electricity. Take one cable leaving a power unit and follow it inward. It runs toward the habitat, but it does not end at the lights. It disappears into the hardware that keeps air moving, water circulating, temperatures controlled, signals routed, and repairs possible. On the Moon, electricity does not remain a convenience layered on top of survival. It becomes one of the conditions survival depends on. That is why continuity matters more than headline generation. People often hear the power problem as a contest between solar panels, batteries, and perhaps a reactor. Those choices matter, but the deeper question is narrower and harsher. What keeps the base alive through ordinary faults, bad timing, and the periods when the surface is least cooperative? A habitat can accept dimmer lighting for a while. It cannot casually accept the loss of ventilation, thermal control, or the machinery that keeps air and water inside workable bounds. Follow 1 watt far enough and you discover that it is doing more than making equipment function. It is holding time open. It is buying the crew enough continuity to diagnose, isolate and repair other failures before those failures spread. If the power chain weakens, troubleshooting itself becomes harder, sensors go dark, pumps slow, communications may be constrained, storage margins begin shrinking while decisions are still being made. The lunar environment makes this unforgiving. Away from carefully chosen polar advantages, the long cycle of sunlight and darkness creates an obvious problem for solar dependence. Even near the poles, the challenge is not solved by finding a bright place and stopping there. Low sun angles mean awkward geometry. A ridge with better illumination may still sit some distance from where the habitat, extraction equipment or shelter wants to be. That means cables, switching hardware, inspection routes and backup paths. It means storage that can bridge shadowed intervals, degraded performance or maintenance downtime. Dust and temperature add their own pressure. A panel that slowly loses performance because its useful surface is contaminated is not simply giving less power, it is narrowing margin. A battery that needs careful thermal management is not a passive reserve. It is a machine whose health must itself be maintained. A connector at the wrong exposed point can turn one damaged line into a wider distribution problem. This is why serious power planning sounds less like choosing a technology and more like planning for fault isolation. What stays alive if one storage bank is taken offline? Which loads can be shed without inviting another problem a few hours later? Can the habitat shelter, communications and environmental systems remain healthy while a cable run is inspected or replaced? Does a rover used for emergency inspection depend on the same weak branch of the network that is already in question? The Moon punishes power architectures that look strong only in their best-case state. That is also why fission surface power receives such persistent attention in lunar planning. Nuclear hardware receives so much attention because it changes the continuity equation. A compact fission system can offer steady output without living inside the same sunlight storage rhythm. On a surface where dark intervals, shadowed work sites, and emergency loads matter, that possibility is enormously important. It also changes the meaning of expansion. If the base wants to add water processing, heavier construction work, more robotics, or longer traverses, it is really asking whether the power system can support new demand without stealing confidence from the old demand. Growth is electrical before it is architectural. A new machine only helps if the base can run it without making the rest of the system feel thinner. But steady output creates its own operational map. A fission unit still has to be transported, deployed, kept at a sensible distance, connected back to the rest of the base, monitored, thermally managed, and approached safely for inspection or repair. If it rejects heat, that heat has to go somewhere. If a fault appears, the crew needs procedures that make sense under lunar conditions rather than in a concept sketch. In other words, a reactor does not replace system thinking. It joins the system as another demanding component. The same is true for large battery farms, regenerative fuel systems, and extended solar fields. Each one can improve resilience in one dimension while creating new maintenance routes, new spare requirements, and new places where dust, thermal strain, or physical damage can start a problem. Power is never alone. It is coupled to the shape of the site, the traffic pattern of repairs, the storage burden of spares, and the question of what the crew can still do when some branch of the network fails. That is why the Bloodstream analogy holds up. The point is not that power is vaguely important. The point is that it moves through everything. If the flow weakens, other organs weaken with it. If the flow becomes more trustworthy, many systems immediately become safer to operate. Building a resilient bloodstream therefore means more than installing a strong source. It means building sensible paths, sensible isolation, sensible reserve margins, and sensible recovery procedures. Once you understand power that way, the quiet equipment rack inside the habitat stops looking secondary. Inside the habitat, many quiet systems are riding on the same promise. Fans, heaters, pumps, and radios all assume the current will still be there during the boring hours, the dusty hours, the shadowed hours, and the repair hours. One hidden power burden is recovery after interruption. It is not enough for a base to survive a fault in the narrow sense of not dying immediately. It has to recover cleanly. Some systems may need a careful restart order. Some may need time to settle before another branch comes back online. A resilient power design therefore includes a philosophy of restart. It asks how to return the base to calm once current has stumbled, not only how to keep current flowing in the first place. That recovery question also reaches into mobility. If a rover is the vehicle used to inspect cables, check shielding work, or reach a dark extraction site, then charging that rover is part of the power architecture, not a side task. A base can easily imagine each system separately. The moon keeps teaching that separation is an illusion. Power is in the room, in the cable outside, in the battery enclosure, in the shelter drill, and in the machine that has to drive out and look for whatever failed. This is one reason power discipline can shape mood across an entire outpost. When the crew trusts the electrical backbone, many other worries become smaller and slower. When that trust weakens, even unrelated jobs begin to feel more fragile. Power is not only a utility, it is the background confidence that lets other systems behave normally. And after power has done its work, the next demand is still waiting. The base must keep a breathable world sealed inside a hull. Start with a seam in the pressure hull. It may be only a line in the structure, interrupted here by a hatch, there by a cable pass-through, somewhere else by a sensor mount or a window. Yet every interruption is doing two jobs at once. It provides access or function, and it asks the wall to remain trustworthy anyway. That is the right way to see a lunar habitat. Before it is home, laboratory, or symbol. It is the structure that keeps an atmosphere where human bodies need one. That changes the meaning of the whole architecture. On Earth, a wall usually separates users. It gives privacy, support, insulation, or weather protection. On the Moon, the wall also holds a pressure boundary against vacuum. A small defect does not stay small for long in the mind of the crew, because the boundary is one of the main reasons the room exists at all. Every seam and interface therefore carries a maintenance future. Someone has to inspect it, trust it, and know what to do if confidence drops. Even the word leak becomes more serious. A leak on Earth can be annoying, expensive, or dangerous depending on the context. On the Moon, a leak is never only a local blemish. It can threaten cabin pressure, consume crew time, force isolation decisions, and turn spare parts into strategic objects. If the leak touches a water loop or thermal path instead of the main atmosphere, the same logic still applies. The crew immediately shifts from living in the space to defending the system that makes the space livable. That is why layout is not a luxury topic. If one compartment doubles as a storm shelter, then its location relative to work areas and airlocks matters. If dirty traffic from EVAs always passes one corridor, then inspection burden and contamination burden concentrate there. If one section can be isolated without sacrificing too much of the base, that isolation capability becomes part of the safety case. Architecture becomes a map of intervention. It quietly declares where the crew expects trouble to arrive and how the base will survive it. The airlock is the clearest example. It is the busiest edge in the whole habitat. Pressure cycling happens there. Dust arrives there. Suits, tools, and samples cross the threshold there. Seals are cleaned there. Mechanical wear accumulates there. If the Moon tests the boundary between inside and outside one hatch cycle at a time, the airlock is where that test is administered again and again. Some designs try to reduce that burden by keeping more of the dirty suit outside the pressurized volume. Others rely on more conventional airlock routines with stronger cleaning discipline inside. Either way, the point is the same. The base must decide where contamination is allowed to live, how much mechanical complexity it wants at the threshold, and what kind of maintenance culture can realistically support that choice year after year. This is why habitat concepts remain genuine trade spaces instead of obvious answers. Rigid modules can be easier to reason about structurally, but they impose one set of launch and volume limits. Inflatable concepts can promise better delivered volume for the same launch envelope, yet they shift confidence toward deployment quality, inspection strategy, and puncture response. Buried or partially buried habitats can improve shielding and thermal stability, but they complicate access, inspection, and some repair paths. Hybrid systems try to move risk between these categories rather than eliminating it. The wrong question is which concept looks most like a future colony. The right question is which concept lets the crew inspect, protect, and repair the boundary with the least dangerous burden over time. A larger interior may sound humane, but a larger interior also means more atmosphere under management, more wall area under concern, and more interfaces to maintain. A buried module may sound safe, but if an exterior problem becomes harder to diagnose once the regolith is in place, that safety has a maintenance cost attached to it. Even windows become less about scenic value and more about whether the exposure is worth the trust it asks of the structure. The same logic applies to micrometeoroids, not because the Moon is waiting with dramatic asteroid impacts, but because exposed hardware lives in a real impact environment. Over time, tiny high-speed hits, thermal cycling, material aging, and dust abrasion all act on the same surfaces. The problem is cumulative trust. Can the crew continue believing the hull and its interfaces after enough cycles, enough inspections, and enough small insults from the environment? Repairability sits right in the middle of that trust. If a section is damaged, can it be reached? If a valve or hatch mechanism begins to wear, can it be serviced without exposing the rest of the base to unreasonable risk? If the best repair still requires outside work, can that work be done with tools and gloves that make sense on the surface? A credible habitat is not simply a strong shell. It is a shell that gives the crew sensible ways to intervene when time, dust, or luck begin to act on it. Inspection matters as much as repair. A wall is only reassuring if the crew can tell when reassurance should change. The moon rewards hardware that can be read clearly before it becomes dramatic. That can be as simple as access panels placed where gloved hands can reach them without gymnastics, or inspection routes that do not require turning every routine check into a minor expedition. A habitat becomes more humane when its safety work can be done without constant strain. Fire safety hides here as well. A habitat interior is a human atmosphere inside a closed system. Materials, smoke, toxic byproducts, ventilation paths, suppression strategies, and cleanup burdens all matter because there is no easy outdoor refuge and no simple opening of a window. Even comfort becomes technical. Every stored fabric, panel, and supply exists inside a pressure-managed environment where contamination and combustion behave differently than intuition wants to believe. Once more, the moon pushes the same lesson. The ordinary interior of human life becomes machinery. A bunk depends on atmosphere control. A meal depends on power, water, and storage. A work table depends on pressure integrity and contamination management. Even sleep depends on the base staying quiet enough mechanically and safe enough chemically that the crew can trust the room around them. A lunar habitat is therefore not best pictured as a house. It is better pictured as the skin of a local world, and skin alone is not enough. Inside that skin, another set of systems has to work with almost boring reliability, otherwise the pressure vessel remains only a shell. The ideal life support system on the moon is not exciting. It hums, circulates, recovers, and reports numbers that stay inside expected ranges. It demands maintenance at known intervals and behaves so steadily that the crew is free to think about other things. That quiet normality is one of the hardest achievements in the entire base. The International Space Station is the natural bridge here. NASA and its partners have decades of experience operating systems for oxygen generation, carbon dioxide removal, humidity control, water recovery, waste handling, trace contaminant management, pressure monitoring, and thermal regulation. Those systems prove something important. Closed or partially closed loops are not fantasy. Human-made ecological machinery can work. But the ISS proves a second thing at the same time. Working loops are maintenance loops. Every gain in recycling tends to arrive with more hardware, more plumbing, more sensors, more filters, more valves, more pumps, more control logic. A base that recovers more water may need fewer imported liters, but it also needs more machinery that can fail. A base that handles atmosphere more elegantly still needs monitoring, replacement parts, and human attention. That is why independence can increase burden even as it reduces dependence. A simple image helps. Bringing bottled water is wasteful in mass, but it is mechanically simple. Recovering water from a loop is efficient in mass, but mechanically richer. You are trading shipped weight for local complexity. On the moon, that trade can be worth making, perhaps even essential, but it should never be mistaken for free abundance. Air works the same way. Breathing on Earth is passive because the planet is doing almost all the work. Breathing inside a base is an active systems outcome. Oxygen has to be generated or supplied. Carbon dioxide has to be removed. Humidity has to be controlled. Trace contaminants have to be monitored and scrubbed. Temperature has to remain inside a band that keeps crew and hardware functioning. Pressure has to be watched, not because someone is paranoid, but because the environment outside is absolute. This means the air itself becomes a maintained machine state. The crew feels normal only because pumps, fans, scrubbers, sensors, and control systems are quietly refusing to drift into abnormality. If any part of that chain weakens, the atmosphere stops being a background condition and starts becoming a troubleshooting event. Water never becomes simple either. Recovery systems can reduce resupply burden, which is crucial. But water loops carry storage needs, microbial risks, filtration burdens, leak risks, and chemical management questions. Waste handling is part of life support, not an afterthought. Used filters, contaminated materials, cargo wrapping, biological waste, and broken components all have to go somewhere. They have to be isolated, processed, stored, reused, or returned. That is why a base needs clear boundaries between graceful operation and brittle operation. Life support can tolerate routine servicing. It can be designed around scheduled part swaps and known inspections. What it cannot tolerate is drift that no one catches because the crew is busy somewhere else. Boring reliability is therefore partly a hardware achievement and partly a culture achievement. Somebody has to trust the numbers because somebody has been doing the work that keeps the numbers honest. The first lunar base is also unlikely to solve food in the romantic way popular imagination prefers. A dome full of thriving crops is a seductive picture because it makes the moon feel settled. But for a serious early base, large-scale agricultural self-sufficiency is far from the main near-term answer. Food may remain mostly imported. Experimental plant systems may exist for science, partial supplementation, or psychological value. But the core promise of a first base is not pastoral independence, it is dependable survival. That brings us back to the quality the whole system is aiming for. Boring. A base needs life support that becomes boring in the best sense. Predictable, repairable, well understood, trusted because it has been maintained through enough cycles that the crew can spend less of their mental life fearing sudden drift. And even then, boring does not mean light. It means racks of equipment. It means spare membranes, pump components, sensors, seals, chemical supplies, software confidence, procedures, logs, and the time to do routine maintenance before routine becomes emergency. The moon makes all of that heavy. Heavy in mass, heavy in planning, heavy in crew attention. This is the part of a moon base that rarely appears in the cleanest concept art. The art shows the module. The real problem is what keeps the module breathable after the novelty of arrival has vanished, and life support has to remain boring across time, not just across a good week. Pumps age, sensors drift, membranes foul, software receives updates, the crew changes, dust finds new routes into the system. A loop that reads cleanly in a design review becomes real only after it has survived enough repetition that people can stop wondering every morning whether today is the day it becomes unstable. That burden is broader than air and water alone. Trace contaminants have to be noticed before they become health problems. Microbial growth has to be watched before it turns a useful loop into a cleaning and safety problem. Waste handling has to stay disciplined so that the base does not quietly poison its own margins. Closed loops reduce imports, but they also create interior ecosystems of pumps, chemistry, and monitoring that demand patience. The crew therefore lives beside a constant background of verification. Numbers are sampled, compared, logged, and trusted only after they have remained trustworthy long enough to earn that trust. When a value drifts, the base has to decide whether the drift is harmless, whether it is the start of wear, or whether it means a repair needs to cut into tomorrow's schedule. Life support becomes boring only after a great deal of unromantic attention. There is a human texture to that attention. If air begins to smell slightly different, if humidity starts feeling wrong, or if the familiar sound of a circulation loop changes pitch, the crew is not simply noticing comfort, they are noticing the condition of the local world. Earth lets bodily intuition sit on top of a huge environmental buffer. A lunar base gives bodily intuition a much shorter leash. Ordinary sensations become part of technical awareness. That is one reason mature life support has to be teachable as well as functional. New crew members must be able to hear the difference between a normal pump cycle and an odd one. They have to know which values matter immediately and which can wait for daylight hours. They have to inherit a culture in which reporting a faint smell, a strange reading, or a small moisture trace is treated as disciplined care rather than nervousness. Boring reliability is partly hardware and partly a social agreement about what counts as worth noticing. Once you see that, another invisible weight comes into view. Not the habitat mass, not the shielding mass, the spare mass. Imagine a storage rack inside the base. It holds the parts nobody wants to need quickly, and everybody expects to need eventually. Replacement seals, filters, connectors, patch materials, electronics, toolkits, rover components, suit hardware, medical stock, containers whose importance becomes obvious only after another system starts misbehaving. That rack is part of the moon base even if no artist ever chooses to dwell on it. A permanent outpost is not sustained only by food and water. It is sustained by the physical inventory of all the things likely to fail, wear, clog, crack, drift, or degrade. Reliability on the moon therefore has shelves. It has labels, tracking, storage rules, and uncomfortable decisions about what deserves a duplicate, what deserves 3 copies, and what has to be repaired in place because carrying enough replacements would cost too much elsewhere. This is one reason launch mass remains central long after the habitat has landed. Every spare part competes for transport, landing, storage space, and protection. A base can reduce some dependence through local resource use and closed loops, but many kinds of precision hardware will still begin their lives on Earth. That means the logistics story is not only about calories and oxygen, it is about sustaining a living inventory of trust. The same logic applies to tools. A repair is only as real as the wrench, patch kit, test device, or cleaning instrument that makes it possible in the moment it is needed. A base can own the right replacement part and still feel exposed if the supporting tools are buried in the wrong locker, contaminated by the wrong task, or wearing down faster than expected. Readiness on the moon is physical all the way down. That physical readiness reshapes the idea of abundance. A full locker is not enough if the wrong kind of failure is still likely to catch the base empty-handed. Good logistics is not a pile, it is coverage, and coverage has to survive time. Some of the most comforting-looking storage may turn out to be the least reliable if it has not been checked, rotated, or protected carefully enough. Lunar logistics is as much about preserving confidence as preserving metal and plastic. The logic becomes sharp when you follow one missing part. If a hatch seal is damaged and the replacement is unavailable, the problem is no longer only a worn seal. It becomes a question about whether that airlock can keep its role in the base safely. If a rover joint fails and that rover was needed for inspection routes, shielding work, or access to an extraction site, then one missing component begins narrowing several operations at once. The moon stretches the consequence of shortage because there is so little background infrastructure to absorb it. Inventory on the moon is also not a simple pile of useful things. Some items are bulky but robust. Others are tiny and central to survival. Some can wait on a shelf for years if protected well enough. Others age while waiting. Batteries degrade, elastomers may not behave the same after long storage. Calibration-sensitive electronics need confidence, not just possession. Protective cases have to survive launch, landing, storage, and the slow intrusion of dust into places nobody invited dust to be. So the spare part room is itself a managed system with failure modes. The International Space Station is again a useful bridge because it shows what mature maintenance culture already looks like in space. Parts are tracked, wear is expected, replacements are planned, hardware health is continuously observed. The lunar version of that culture would be harsher because it adds dust, more difficult outside work, longer logistics delays, and fewer chances to treat Earth as a fast answer. It also means the base has to become good at audits. Operators need to know which shelf is drifting toward shortage, which components are aging out quietly, and which repair paths are consuming more tools or seals than expected. An inventory system that is vague or optimistic is dangerous because it hides weakness until the wrong item is suddenly gone. Forecasting becomes almost as important as storage. A part that fails once is one story. A part that begins failing a little faster every month is another. If a certain kind of seal or filter starts being consumed ahead of plan, the base has to decide whether that means the storage model was wrong, the operating tempo was too aggressive, or another unseen problem is creating extra wear. The shelf is not passive, it is evidence about what the rest of the outpost is secretly demanding. Crew time belongs on the same ledger as spare mass. A spare part in a locker does nothing by itself. Someone must diagnose the fault, find the correct item, isolate the right system, perform the swap, test the result, log the change, and decide whether the removed component can be refurbished, stored for analysis, or retired. Maintenance is not only a materials burden, it is a time burden. It also becomes a judgment burden. If one kind of filter is being consumed faster than expected, do operators keep the same activity level and trust later resupply, or do they throttle the dusty work that is driving the burden? If a patch is technically possible but no longer fully trusted, does that component remain in service as a backup, or does it leave the active system before it can seed a larger problem later? The Moon rewards people who think like operators, managing margin, not only like builders finishing tasks. This is one of the easiest truths to underestimate from Earth. We like to imagine astronauts on the Moon doing science, driving across ridges, drilling, prospecting, and making discoveries. A functioning base may do all of that, but it has to earn those hours. If cleaning, inspection, replacement, and troubleshooting keep expanding, then the crew becomes the nervous system of a workshop whose first task is preserving itself. That is not failure, that is the actual work of permanence. There is also a temptation to imagine cannibalization as a clever backup plan. On paper, it sounds efficient. Take a non-critical system apart to keep a critical one alive. But cannibalization is really a confession that the spare inventory was thinner than the architecture needed. It may save a mission phase. It rarely feels like stable permanence. A credible base wants repair trees that do not constantly solve today's problem by quietly manufacturing next month's weakness. Emergency logic belongs here as well, but in a practical way. A first base may depend on return capability, a protected refuge, redundant stores, or a carefully isolated shelter volume to keep a single fault from threatening the entire crew at once. Those protections are not separate from logistics. They are logistics expressed as survival margin. If return is easy, one architecture may look acceptable. If return is delayed or temporarily impossible, the stored confidence inside the base has to deepen. Medical stock tells the same story from the human side. The inventory does not end with pumps and cables. It also includes pharmaceuticals, sanitation materials, diagnostic tools, trauma supplies, and whatever quiet equipment becomes essential when bodies are living far from immediate help. Human vulnerability has mass too. All of this hidden mass changes the emotional picture of a moon base. It is not a single habitat lowered onto a prepared site and left to symbolize the future. It is a continuing stream of sustaining matter, much of it arriving in containers whose importance becomes obvious only when something fails at an unhelpful hour. That is exactly why local resources are so attractive. If the Moon can supply some of what the base would otherwise launch from Earth, the mass ledger begins to loosen. But that hope only matters if the resource can survive being turned into a real supply chain. There may be water on the Moon in forms and places that matter a great deal. That statement is now solid enough to shape real plans. Data from multiple missions and observations have built a serious case that lunar water or hydroxyl-related signatures exist, especially at the poles and in permanently shadowed regions, while other observations have added nuance about molecular water in sunlit areas. The broad lesson is that water is part of the lunar story. But broad lessons do not fill tanks. This is where the mind needs a hard distinction. Finding evidence of water is not the same as having a water supply. The difference is not semantic, it is industrial. A supply means prospecting, excavation, processing, capture, purification, storage, distribution, leak management, quality control, maintenance, and power. A detection tells you where the work might be worth attempting. It does not mean the work has already been done, Prospecting alone is a discipline. Before a base can count on local water, it has to know where usable material actually is, how deep it sits, how concentrated it may be, how patchy the deposit is, and how those answers vary across terrain that may be difficult to revisit often. A misleading map does more than waste time. It can distort the entire resource strategy of the settlement. That is why orbital evidence and local truth are not the same thing. A promising signal from above still has to survive ground contact. The base needs tools that can sample, compare sites, and keep returning enough consistent information that operators believe the extraction plant is being built in the right place. Otherwise, the moon offers something worse than scarcity. It offers false confidence. That matters because water is unusually valuable. The same material may end up supporting very different needs inside one outpost. Water clean enough for the crew is not the same thing as water useful as shielding mass or process feedstock. The consequence is simple. A water detection is not one answer. It is the beginning of several competing plans, all of which depend on how much water is truly there and how hard it is to handle. A permanently shadowed crater is a good example of this double truth. Its cold darkness may help preserve volatiles. That is why those regions attract attention. But the same cold darkness makes extraction hard. Machinery may need to operate where sunlight is not directly available. Communication geometry may be awkward. Terrain may be difficult. Components have to tolerate extreme thermal conditions while also dealing with dust, wear, and a need for repeated performance, rather than one triumphant demonstration. So the sequence becomes long very quickly. At the start it may look like a mining problem. Then it turns into a hauling problem, then into a thermal problem, because cold material may have to be heated or otherwise processed to free what the base wants from what the soil is holding. Then it becomes a storage problem, because captured water has to stay in trusted containers instead of escaping into leaks, contamination, or losses the crew cannot afford. By the time the first useful supply reaches the habitat, the base has already built an entire chain of specialized work around a resource that began as an orbital clue. That is not a faucet, that is a plant. And a plant on the moon is just another exposed machine joined to the rest of the exposed machines. This does not reduce the importance of lunar water. If anything, it makes the stakes clearer. A difficult resource can still reorganize a whole architecture. A habitat may be placed differently because of it. A power system may be sized differently because of it. Logistics may be planned differently because of it. Water matters precisely because it refuses to matter simply. Purity matters as much as quantity. Water that ends up inside life support may need different handling from water used for shielding or industrial chemistry. If volatile-bearing material arrives mixed with other compounds, then separation and quality control are not optional finishing touches. They determine what the output is actually good for. The base may not be harvesting a single clean resource. It may be running a process stream that needs triage, testing, and careful routing. But hope has to remain disciplined. The moon does not reward the sentence "there is water there" with the simpler sentence "so the base will have water." Between those two statements lies one of the most demanding engineering ladders in the whole project. Water also reveals the base as a place where uses compete. The crew may want some volume protected as emergency reserve. Other teams may want more of it kept in circulation, so the extraction system keeps proving itself. That tension is healthy if it is visible. It is dangerous if the base talks about water as though every liter is interchangeable. On the moon, value depends on where the water is, how clean it is, and what risk the crew is willing to take with it next. The deeper point is this. Storage turns out to be another quiet challenge. A water supply has to remain where the base expects it to be, in containers the crew trusts, at temperatures and pressures that do not create a new hazard. It has to be measurable. It has to be protected against leaks, contamination, and wasteful loss. In a place where every kilogram matters, even the tank becomes part of the engineering story. The moon may help a base become less dependent on Earth, but helping is not the same as replacing. at least not in the early operating years. Local resources are best understood as a way of reducing some import burdens over time if the extraction systems themselves become dependable enough to trust. And even when the water starts arriving, it still has to be allocated. One portion may matter most as protected reserve, another portion may be better used elsewhere in the architecture. One resource begins serving several masters at once, which means the base has to become good at saying which use matters most today and which use can wait, and that if is enormous. The Moon may eventually offer a path toward lower dependence on Earth, but early on the more honest picture is narrower. Local water can become a strategic assist before it becomes a full local answer. A base may use it first to reduce selected imports, to build confidence in extraction methods, or to support shielding and operational reserves at modest scale. Those are still major achievements. They simply are not the same as turning the lunar surface into a turnkey supply chain, because before a base can rely on local water, it needs the infrastructure that protects landings, manages dust, moves material, and creates working surfaces for all the machines already mentioned. In other words, construction is not what comes after survival. Construction is part of survival. The first permanent-looking thing on the Moon may not be a habitat. It may be a landing pad. That sounds disappointingly practical until you ask what repeated landings do to loose regolith near exposed hardware. Rocket exhaust interacting with the surface can kick dust and ejecta outward toward whatever the base is trying to protect. A radiator does not care whether the incoming damage came from nature or from the base's own traffic. A solar surface, suit interface, sensor, or exposed joint only experiences abrasion. So a real outpost may need to prepare the ground before it can safely expand. This is one of the clearest differences between touching down once and beginning to stay. A single landing proves access. A site that can accept repeated arrivals without sandblasting itself is already something closer to infrastructure. The Moon asks for surface discipline before it grants the feeling of permanence. That discipline extends beyond the pad itself. A durable base needs roots that keep rovers from endlessly spreading contamination through the same fragile zones. It needs places where regolith can be moved, piled, or compacted without constantly threatening hatch areas and thermal surfaces. It needs separation between incoming vehicles and the equipment those vehicles would otherwise damage. Growth without that discipline only enlarges the field of self-inflicted wear. Verification matters here as much as construction. A finished-looking pad is not enough. The real question is whether repeated landings actually stop throwing damaging material toward the hardware that matters. A berm is not useful because it resembles infrastructure. It is useful if inspection shows that the radiator, sensor mast, or nearby hatch is living a gentler life because that berm is there. A prepared route earns its mass only when the crew feels the difference in cleaner returns, lower wear, or faster work. That requirement continues after the first success. A pad that survives one landing still has to be checked after the next one. A route that seems clean in one season still has to prove it is not quietly sending dust into the same maintenance bottleneck by another path. Lunar construction becomes a conversation between hardware and evidence. The surface has to show that the work truly changed operations, not merely that the work looked finished from a distance. This is where the famous phrase "use the regolith" starts to become more demanding. The attraction is obvious. The Moon is covered in material and launched mass is expensive. Yet the first valuable question is not whether soil exists, it is whether the base can move that soil in the right quantities, to the right place, often enough to change operations for the better. A loader that works once is a demonstration. A loader that still works after weeks of abrasive contact and awkward maintenance is infrastructure. That is why Earth moving on the Moon behaves less like free local abundance and more like a negotiated truce. Each bucket of moved material costs wheel wear, power, operator attention, and another round of inspection on the machinery doing the job. If the digger becomes unreliable, the whole argument for local leverage weakens immediately. The site has not only to contain useful mass, it has to let the outpost keep turning that mass into protection without exhausting the machines that perform the conversion. This is why autonomous preparation remains so attractive and so difficult. In theory, robots could arrive first, shape a safer landing area, move shielding material, and create a more forgiving surface before long-stay crews arrive. In practice, those robots have to work long enough and clearly enough that people are willing to trust what they prepared. If the machine that builds the pad becomes the first major repair burden, the advantage shrinks quickly. The same problem appears when power and communications are routed across the site. Cables may need trenches or protective routes. Navigation markers may need to survive both dust and repeated traffic. Storage zones may need to sit far enough from active landing areas to remain useful after arrival, but close enough to be worth the handling burden. Construction decisions become survival decisions, because later operations inherit whatever geometry the first builders leave behind. Laboratory success and dependable fieldwork are therefore different achievements. A demonstration that regolith can be compacted, sintered, printed, or piled tells us something important. It does not yet tell us that a base can rely on the result after repeated use, repeated landings, and repeated wear. Real infrastructure has to stay where it belongs, keep doing the job it was built to do, and remain inspectable when doubts appear. Otherwise, it becomes one more object the base has to worry about instead of one more problem it has solved. That is why construction wins have to age well. The surface keeps asking the same rude question: does this still work after the first excitement is gone? That question applies to human trust too. Crews start treating a route, pad, or berm as real infrastructure only after enough ordinary use has passed without new surprises. The moon does not grant confidence at inauguration. It grants confidence slowly. This is civil engineering, but under frontier conditions. It is also sequencing. Perhaps one landing zone must be prepared before the main habitat arrives. Perhaps shielding work has to happen before sensitive systems are fully exposed. Perhaps traffic rules and cable paths must be established before rover activity multiplies. Each phase changes the safety of the next one. The base is built through partially secure states that have to become slightly more secure before expansion continues. That makes early lunar infrastructure feel less like architecture and more like a chain of temporary treaties with the surface. One machine stabilizes the ground enough for another machine to land. One prepared route protects the rover long enough for shielding mass to be moved. One berm lowers the risk enough for sensitive hardware to remain in place during the next phase. Permanence arrives through a sequence of modest improvements that must all survive contact with the same unforgiving dust and vacuum. That may sound less inspiring than images of domes and skylines, but it is the kind of seriousness permanence requires. Pads protect habitats. Routes protect vehicles and crew time. Berms protect hardware. Shielding placement protects the shelter that protects everything else. Construction is not what comes after survival on the moon. Construction is one of the ways survival is made possible, and construction changes morale as much as geometry. A route the crew trusts, a landing zone that no longer feels reckless, or a berm that has clearly spared a vulnerable surface gives the outpost something priceless. Fewer unpleasant surprises. Infrastructure becomes a way of lowering the emotional tax the environment imposes on every ordinary task. And once those surfaces, routes, and protections begin to hold, the outpost starts to resemble something more industrial than symbolic. It starts to resemble a workshop, and that resemblance is a kind of progress. A symbolic outpost can look beautiful while still feeling precarious. A workshop may look less glamorous, but it means the settlement has begun organizing itself around repeatability rather than display. That change could alter how the crew understands achievement. The first months of a base may be measured less by dramatic exploration range and more by how quietly the support systems behave while useful work continues. A settlement that feels calmer after a hard week has learned something real about staying alive there. That calm would not be empty. It would create room for better science, better exploration, and better judgment. When the crew is not constantly rescuing the support system, they can finally ask larger questions with more patience. The workshop is not what distracts from discovery, it is what makes discovery sustainable. A moon base becomes intellectually useful only after it becomes operationally steady enough that curiosity is no longer fighting panic for the same hour. That may be the most practical definition of permanence. Not endless comfort, not giant scale, just enough steadiness that the crew can keep choosing tomorrow's work instead of merely surviving today's interruption. When a base reaches that state, it stops feeling like a visit that forgot to end. It begins feeling like a place with memory, routine, and enough margin to think ahead. That is when staying finally becomes more than surviving. It becomes a durable human routine. Imagine a maintenance board at the start of a lunar day shift. A board like that may show a pressure trend that needs watching, a rover battery that needs charging, an airlock inspection that cannot slip, and a water loop anomaly that has to be understood before the next outside task begins. That board may tell you more about a moon base than any panoramic exterior. Permanence on the moon is not expressed mainly as adventure, it is expressed as repeatable work that keeps the system inside safe limits. Somebody checks the interface that was dusty yesterday. Somebody verifies that a shelter route remains clear. Somebody confirms that a rover can still be trusted for the job assigned to it. Somebody looks at yesterday's irregular number and decides whether it is noise, wear, or the beginning of a larger problem. This is what it means for the base to become a workshop, not a metaphorical workshop, a real one where survival depends on tools, logging, inspection, repair, planning, and the discipline of preventing small problems from joining together. The emotional rhythm of such a place would be shaped by dull signals that matter, a changed fan sound, a hatch that resists closure a little more than usual, a wheel that comes back carrying more dust than it did last week. The point is not to make everyone anxious. The point is to keep the base teachable. Small clues have to stay small long enough for somebody to read them clearly. That habit changes the meaning of expertise. The most valuable person in the room may not be the one delivering the most dramatic scientific insight that day. It may be the one who notices the pressure curve drifting in a familiar but unwelcome way, or the one who remembers that the same seal was cleaned twice in the previous week, or the one who sees that today's construction plan will overload the same power branch needed later for thermal recovery. Workshop culture is not glamorous, but it is how a base keeps earning tomorrow. That culture also depends on memory. Logs are not paperwork for their own sake. They are the base's second nervous system. They tell the next shift which valve was temperamental yesterday, which rover route brought back too much contamination, which filter loaded earlier than expected, and which repair is beginning to repeat often enough that the design itself may need to change. A workshop that forgets cannot improve, it can only react. Robots belong in this picture, but not as magic labor. They can inspect, haul, scout, move regolith, and reduce some human exposure. That makes them valuable. It also makes them another class of machine whose needs now matter. A critical robot requires charging, communications, protected storage, spare components, software confidence, and hardware that tolerates dust well enough to stay useful. If robotic help becomes essential, robotic upkeep becomes part of base life. That does not weaken the case for robotics. It clarifies the cost of capability. A moon base grows by adding workers, human or robotic, who themselves must be supported by the rest of the system. The workshop expands because the workforce expands. The workforce expands because the workshop already exists. Each layer of help creates another layer of maintenance and planning. Crew time is therefore one of the most human forms of scarce resource. If too much of the schedule is spent recovering from backlog, then science, exploration, prospecting, and construction all begin losing ground. The base may remain technically alive while becoming operationally brittle. Rest, training, and the ability to think ahead are part of resilience because tired people make weaker maintenance decisions. On the Moon, fatigue can be converted directly into system risk. This is why science time has to be defended operationally, not just promised rhetorically. A base that wants more exploration must keep maintenance predictable enough that rovers are ready when needed. A base that wants more construction must make sure construction work is not draining the same power, tools and crew hours required to keep the habitat calm. Ambition survives only if the workshop underneath it remains orderly. This is why maintenance culture is not an embarrassing side story. It is the backbone of lunar credibility. A base that cannot preserve time for its larger mission is not yet operating at a level worthy of being called dependable, no matter how advanced its modules look from orbit. The workshop has to become efficient enough that life is not consumed by the defense of life. Tool design belongs in the same practical frame. Handles must work with gloves. Fasteners must remain serviceable when dust is present and visibility is poor. Diagnostic displays must tell the truth clearly under stress. A workshop on Earth can lean on convenience and easy replacement. A workshop on the Moon has to be designed around friction from the start. That makes the base less romantic and more interesting. You can read the whole system by following one maintenance task outward. Clean an airlock seal and the job does not end at the brush. You ask how often that seal is getting dirty, whether EVA temper has changed, whether filters are loading faster, whether the same corridor is carrying too much contamination, whether spare seals are falling behind plan, and whether the crew is now stealing time from another critical job. The workshop is where every simple task reveals the wider architecture behind it. It is also where realism enters the dream. The first serious moon base may not feel like a frontier town at all. It may feel more like a careful industrial platform whose people are trying to win back enough reliable hours each week to do science, prospecting and building without compromising the life support machine underneath them. That is not a lesser vision. It is what early permanence actually sounds like. The romance does not disappear. It simply moves. It moves from the dramatic moment of arrival to the quieter achievement of making tomorrow feel stable enough that exploration can happen on purpose instead of by luck. And once they are visible, the final lesson of the base becomes hard to ignore. The challenge is no longer any single hazard by itself. The challenge is the way the hazards and the solutions keep pulling on one another. Take the dusty airlock seal from the opening and do not let it stay small. Let it connect outward. Dust on the seal means more cleaning. More cleaning means more crew time and more procedures. More contamination risk means more filters and replacement seals. More replacement parts mean more mass from Earth. More stored mass means more habitat volume, storage planning, and landing logistics. If the base grows, more EVAs may increase dust exposure again. A single interface becomes a chain. That is what coupling means on the Moon. Not merely that the systems are related. Of course they are related. Coupling means that solving one problem changes the shape of another. Every improvement arrives as part of a network of consequences. Radiation offers a second chain. If you want better protection, you may add shielding mass. If the shielding comes from regolith, then you need excavation and transport capability. Excavation and transport need power. They need machines that survive dust and thermal stress. Those machines themselves need maintenance, spares and storage. The act of building better shelter therefore increases demand on the very base whose shelter you are trying to improve. That does not make the effort pointless. It makes it systemic. Water gives us a third chain. Suppose nearby polar resources are real enough to exploit. Good, then the base may eventually reduce some dependence on Earth. But to exploit them, it needs prospecting, excavation, power in difficult terrain, communications, processing hardware, storage tanks, contamination control, maintenance, and a way to move the resulting water or derived products into the life support architecture. A local resource lowers one dependency by adding another structure of dependencies around itself. This is why there is no single villain in the moon base story. It is not simply dust, not simply radiation, not simply power, not simply money, not simply rockets, not simply water. Those are pieces. The deeper difficulty is that the moon rewards no isolated fix. Each remedy becomes another machine joined to the rest of the machines. That truth is easy to miss when problems are presented as lists. A list says, here are the obstacles. A coupled view says, here is the network that keeps turning obstacles into operating behavior. That shift matters because it changes what progress looks like. Progress is not the first successful power system, or the first successful excavation test, or the first successful resource processing run, or the first successful buried module. Progress is the point where several of those things begin surviving one another, where improvements in one area do not create unmanageable weakness in another, where the base stops acting like a stack of demos and starts acting like an ecology of dependable hardware. This is also why integrated testing on Earth is useful, but never fully sufficient. Simulations, analog habitats, vacuum chambers, dust studies, and field robotics trials can reveal a great deal. Yet the full truth of coupling appears only when systems begin sharing one harsh environment and one finite crew for long enough that trade-offs become operational instead of theoretical. The moon is not merely a test location, it is the final integrator. That is why maturity on the moon may first appear as reduced surprise. Repairs begin taking roughly the amount of time the planners expected. Filters last about as long as the trend suggested. Power reserves recover in the pattern the operators trust. A site becomes credible when its couplings are no longer mostly hidden. The crew starts to know where one problem will spread before the spread begins. You can see that in one ordinary repair. A dusty seal may force extra cleaning. Extra cleaning spends crew time and filters. Spending that time may postpone rover inspection. Postponing the inspection may delay shielding work or prospecting. Delaying that work may keep the base more dependent on Earth for longer. The important point is not drama, it is that the lines connect. The moon turns a local maintenance event into a systems question very quickly. This is also the best reply to the belief that one breakthrough could make the whole question easy. A better rocket helps. A cheaper launch system helps. Better batteries help. Better dust mitigation helps. Better robotics help. Better in-situ processing helps. But each of those helps by easing part of a network, not by dissolving the network itself. The moon remains the kind of place where ordinary needs become linked engineering burdens. That is why a moon base is so instructive even if one never gets built at city scale. It forces human ambition to deal with coupled reality in a clean, visible way. You cannot hide from the chain, you cannot talk around it. Air needs power, power needs hardware. Hardware needs maintenance. Maintenance needs spares. Spares need logistics. Logistics need landing systems and surface infrastructure. Infrastructure needs construction. Construction needs power and machines. Machines live in dust. Round and round the base goes, but not in circles. That is important. This is not circular because each loop reveals a real dependency that can be improved, tested, or redesigned. The challenge is not meaninglessness. The challenge is integration. A serious lunar architecture has to show not just how each element works in isolation, but how the whole system keeps working after the first few victories fade into ordinary operation. When that happens, progress begins looking quieter and more believable. The best month may be the month in which fewer problems spread. That is the standard concept art rarely has to meet. A clean rendering only has to look plausible for a moment. A base has to stay plausible after the 1000th dirty hatch cycle. The same logic applies to economics. Launch cost matters because every dependency has mass, but the bigger story is not just price per kilogram, it is whether the kilograms being sent create a system that becomes progressively calmer, or a system that remains trapped in heroic upkeep. Cheap launches can feed a bad architecture as easily as a good one. Coupling decides whether the added mass becomes resilience, or just more things to maintain. So the hard part is not defeating the moon in one dramatic stroke. It is teaching a growing set of machines to support one another without multiplying fragility faster than they create capability. That is a quieter achievement than a first landing. It is also the one Permanence actually requires. It also means good news can be subtle. A better month on the moon may not look like a new skyline. It may look like fewer emergency cleanups, more predictable energy use, shorter repair windows, or a resource system that finally behaves the way the team expected last season. Those quieter improvements are exactly how coupling begins to move in the right direction. Once you understand that, the question changes one last time. It is no longer only what stops us from building a moon base. It becomes what would make one credible. A credible moon base may look smaller and less triumphant than many people expect. That is not a disappointment. It is a sign that the base has started answering the right question. If you judge by spectacle, scale wins. More modules, more rovers, bigger layouts, cleaner renderings, perhaps a sense that the moon has already been tamed. But if you judge by operational honesty, credibility comes first. Can the habitat hold pressure dependably? Can the crew shelter from radiation with real margins? Can dust be managed instead of merely tolerated? Can life support stay stable without constant drama? Can the power system survive faults? Can landing traffic occur without ruining nearby hardware? Can the base repair itself faster than it degrades? Credibility grows in steps. One reliable landing zone matters, then a second proven cycle matters. A shelter that remains ready after repeated use matters. An extraction tool that still performs after the first maintenance season matters. A stock system that predicts shortages before they become crises matters. The base becomes believable by surviving repetition, not by sounding large on paper. Those are smaller questions with larger consequences. They suggest that the first serious base should not be imagined as the first lunar town. It should be imagined as the first lunar system that can keep winning after the landing itself is no longer impressive. Reliability, therefore, matters more than beauty. A modest habitat with dependable power, a protected refuge, disciplined dust control, a safe landing zone, and a well-stocked maintenance culture would be more real than a larger architecture that has not yet proved those things under lunar conditions. Credibility lives in margins, not in silhouettes. Technology demonstrations are still essential, but they must be placed correctly in the ladder. A credible program would probably advance through phases that look modest from the outside and revolutionary from the inside. First, prove that a surface habitat and power system can remain stable for longer stretches. Then prove that dust control, shelter logic, and maintenance routines survive repeated use. Then prove that landings can continue without harming the settlement. Then prove that local construction or resource systems reduce dependence instead of merely adding complexity. Each phase earns the right to enlarge the next one. One successful excavation test matters. One successful surface power test matters. One successful resource processing run matters. One successful shielding experiment matters. But none of them alone establishes a base. Each is a rung. The ladder only becomes convincing when those rungs begin connecting into repeatable operation. That repeatability has an emotional signature as well. Early in any architecture, every success can feel fragile and overinterpreted. Later, a quieter kind of confidence matters more. The second, third, and 10th repetition tell the real story. A base becomes believable when another safe landing, another routine shelter drill, or another ordinary maintenance cycle stops feeling miraculous and starts feeling expected. Can the equipment be inspected and repaired? Can the task be repeated under the same harsh conditions? Can the crew depend on it rather than admire it? That is the transition from demonstration to presence. Credibility also demands a dependency map. A real plan has to admit what still comes from Earth, what is expected locally, what the crew does when a critical subsystem fails, and how safe haven or return logic fits the rest of the architecture. The more honestly those dependencies are drawn, the more believable the base becomes. That map should include failure tempo as well as hardware layout. Which systems can be down for hours, which can be down for minutes, which need graceful degradation instead of full shutdown, which spares have to be on hand before a mission even launches because waiting for resupply would change the risk category too much. A credible base is one that has already asked those questions before the emergency forces them. This is where cost and governance may enter, but only as supporting consequences of physics. Shared polar sites matter because useful light and useful resources may be clustered. Operational rules matter because landing zones, contamination, rescue expectations, and communications are not abstract legal puzzles once humans are actually living there. Cost matters because the environment demands redundancy, protective mass, spare inventories, and infrastructure before romance can scale. But these are secondary truths. The primary truth is still physical. A credible base is one whose ordinary systems have been made trustworthy enough that the extraordinary act of living there starts to settle into routine. That routine will probably look humble: frequent inspections, conservative expansions, careful site management, a base that says no to attractive but destabilizing activities until the underlying support system is ready. Humility is not the enemy of lunar permanence. It is one of its strongest design tools. That is a high bar, and it should be. The moon is close enough to tempt overconfidence. Its visibility in our sky and its deep place in human imagination can make it feel like a destination already half claimed. Credibility is the discipline that resists that feeling. It asks not whether humans want to be there, but whether the machine meant to keep them alive there has earned trust. Perhaps that is the cleanest way to frame the whole subject. A moon base does not become real when the drawings improve. It becomes real when the uncertainties shrink inside actual operations. When dust control is not a hope but a practice. When shielding is not a sentence but a built condition. When power continuity survives a bad stretch. When spare management and crew time are no longer hidden assumptions, when local resources help enough to matter without being overclaimed. When the base begins to look less like a one-off stunt and more like a small, stubborn organism. That does not require grandeur, it requires honesty. It also requires patience with boring milestones. A power network that survives another season of operation may matter more than a dramatic expansion sketch. A dust barrier that measurably reduces contamination may matter more than another flashy rendering. A logistics model that proves the spare burden is manageable may matter more than a broad statement about humanity's destiny. Credibility grows by surviving reality, not by sounding large. It also requires a plan that admits what still comes from Earth, what must be stored locally, what can fail without ending the mission, and what the crew does next when one assumption breaks. A credible architecture does not hide dependency, it maps it. That honesty is what allows later independence to be earned rather than imagined. It also gives engineers permission to stay small on purpose. A modest first habitat with proven routines can be a stronger beginning than a sprawling architecture whose hidden dependencies have not been made explicit. On the moon, restraint is not timidity. It is a design choice that protects the next step from being built on theatre instead of trust. That restraint may even improve ambition in the long run. A base that knows exactly what it can maintain is in a better position to grow than one that has promised itself too much too soon. Expansion built on honest margins can survive. Expansion built on performance often has to be rescued by the very systems it refused to respect. Patience is therefore not the opposite of boldness here. It is one of boldness's most useful tools. It also protects credibility from hype. If a base expands only after the old burdens are well understood, each added module or machine arrives in a system that knows how to absorb it. That may be slower than the public fantasy. It is also how a foothold stops being theatrical and starts becoming trustworthy. And once that honesty is in place, the closing answer becomes simpler, though not easier. The moon is not beyond us. It is just less forgiving than our first glance wants to believe. Return to the airlock seal. At the beginning, it looked like a small practical detail, some dust on the edge of a hatch, something to brush away before pressure comes back into the module. Now the same seal carries the whole base with it. Dust has reached it, which means the problem is already larger than one hatch edge. A dirty seal points backward toward EVA tempo, toward the route the crew took home, toward the brushes and covers that may or may not be doing enough, and toward the filters that will have to catch whatever still made it inside. It points sideways toward power, because cleaning stations, air circulation, and diagnostics all rely on electricity that keeps arriving when promised. It points upward toward shielding and shelter, because the people caring for the seal are themselves living inside a structure that has to remain trustworthy against radiation, wear, and time. And it points outward toward logistics, because every answer eventually asks what has to be replaced, repaired, or carried from Earth. That is why there is no single villain to defeat. Rockets are not enough, money is not enough, water is not enough, solar panels are not enough, nuclear surface power is not enough, regolith shielding is not enough, robots are not enough. Each one matters, none of them stands alone. The moon keeps forcing the same correction. Living there is not one breakthrough. It is the earned alignment of many imperfect systems. This is easy to flatten into the sentence space is hard, but that sentence is too blunt to be useful. It hides the more interesting truth. The moon is hard in a very particular way. It is close enough that we can imagine ordinary habitation, which is why disappointment comes so easily when the hardware refuses to behave like a neighborhood. It is hostile enough that ordinary habits have to be rebuilt as machinery, procedure, and margin. It allows landing, but it does not reward complacency after landing. It offers possible resources, but only inside difficult industrial work. It offers local material, but only after machines turn that material into something protective and dependable. The result is not impossibility, it is conditionality. Those conditions are practical. They live in the kind of questions operators ask during tired hours. If one volume has to be isolated, does the rest of the base stay calm enough to live in? If one rover is down, does another route remain for inspection or shelter access? If extraction pauses, does the architecture remain stable, or does confidence in several other plans begin to wobble at once? If a week of heavy outside work leaves too much dust and too many deferred checks behind it, can the crew recover without turning the next month into cleanup? The moon keeps translating big ambition into these quiet tests of procedure. A moon base becomes believable only when the conditions that keep people alive stop depending on brief heroics and start depending on dependable systems. When the base can close the hatch again tomorrow, when the seal still works after long repetition, when the shelter is real, when the air remains ordinary because the machinery stays boring, when the crew is not spending every hour rescuing the outpost from its own fragility, when the base has enough margin to survive being a place instead of merely surviving being an event. That may be the clearest difference between landing and staying. Landing is a peak experience. Staying is a maintenance culture. That difference changes what success should look like in our imagination. A successful base is not one that produces the best poster. It is one that makes ordinary days feel trustworthy. It is one where the crew believes the next hatch cycle, the next shelter drill, the next repair window, and the next shipment can all be absorbed without the whole place becoming anxious. Trust is the real architecture. Apollo gave us the first kind of triumph. A future moon base, if it comes, will need the second kind. Less cinematic, perhaps, far more revealing, because if humans do learn to live on the moon in any serious sense, the achievement will not be that we reached a nearby world once again. It will be that we built a system capable of enduring all the unglamorous pressures that the nearby world kept applying after the applause was over. That is why the engineering answer is more compelling than the mythic one. A myth says the moon is waiting for a bold return. The engineering answer says the moon is waiting for a culture of design, maintenance, logistics, and restraint strong enough to hold a human world together where nothing outside that world is helping by default. That is what stops us for now. Not a lack of courage, not even a lack of imagination, a lack of enough integrated, trustworthy, repeatable infrastructure to make a local human world hold together on a surface that never becomes gentle. And that answer may be more exciting than the fantasy it replaces, because it means the moon is not closed. It is simply honest. It demands that human presence be earned at the level of real interfaces and real routines. Seals have to keep closing well. Filters have to stay ahead of contamination. Power has to remain continuous through ordinary faults. Extraction systems have to justify the burden they add. And the crew has to keep treating every ordinary task as part of the larger machine. The moon hangs above Earth, looking familiar enough to invite us back. A first serious base will probably answer that invitation in a humble form. It may include a return option. It may lean heavily on stored spares and a protected refuge. It may look more like an industrial camp with excellent procedures than a second world in miniature. That should not disappoint us. It should remind us what the real achievement is, building enough trust in the machinery that life on the surface can continue after the spectacular part is over. If the first durable habitat feels cautious, that caution will be evidence of maturity, not of failure. But familiarity is not forgiveness. Close does not mean easy, and a base does not begin when people land. It begins when the systems can keep them alive after landing is no longer the achievement. See the base again now, not as a city sketch, not as a lonely module dropped onto grey ground like a symbol. See the smaller, harder picture. A habitat near the South Pole, dust at the threshold, a cable feeding power into the pressure volume, a radiator facing a sky with no atmosphere, a rover parked outside carrying wear home from the terrain, regolith piled where shielding needs mass, spare crates positioned where repairs can reach them. At the beginning, that scene looked mostly like distance. Now it should look like continuity. Apollo proved humans could reach the moon and work there. What it did not prove was that a local system could stay healthy there through repetition. That is the unanswered part. A base has to keep ordinary life going under conditions that never become ordinary. Pressure must hold. Air must remain safe. Water must circulate. Power must continue through bad hours as well as good ones. The shelter has to stay trustworthy while dust, radiation, cold, wear, and simple time keep pressing on the hardware. The important thing is that none of those pressures stays inside its own box. Dust reaches seals and filters. Seals protect pressure. Pressure makes the habitat meaningful. The habitat depends on power. Power depends on generation, storage, routing, and repair. Shielding may depend on moved regolith, which depends on machines that can survive dust and keep drawing power. Water may reduce imports, but only after prospecting and processing systems prove they can survive the same surface that threatens everything else. Every solution enters a network. That is why the moon still resists casual settlement, not because it is unreachable, because staying there is a systems problem with almost no room for pretending that one strong idea can stand in for the rest. A serious first base will probably look smaller, rougher, and more maintenance-heavy than the public dream. That would not mean ambition failed. It would mean ambition matured. Real permanence begins with the parts that keep working after the exciting phase ends. The trusted hatch, the stable life support loop, the shelter that remains ready, the power chain that keeps its margin, the spare stock that prevents a small fault from becoming a crisis, and the routines that preserve enough schedule for science and exploration. Seen from Earth, that can sound unsatisfying because the human imagination loves visible expansion. But the moon may teach the opposite lesson first. The true victory may be a week in which nothing dramatic happens because the systems were good enough, the crew was disciplined enough, and the site was organized well enough that small problems stayed small. That kind of calm is easy to underestimate. It is also the calm on which every larger dream would depend. That is the useful picture. A moon base is not a building waiting to be funded. It is a coupled survival machine waiting to become trustworthy. If one day humans really do stay there, the achievement will not be that they landed again. It will be that they learned how to keep a local world functioning after landing was no longer the headline. Until then, the answer remains plain. What stops us from building a moon base is not one missing invention. It is the stubborn fact that the moon turns every ordinary need into machinery, every machine into maintenance, every maintenance burden into logistics, and every shortcut into another test of whether the whole system can truly hold together. That is why the question is worth asking so carefully. It does not only tell us something about the moon, it tells us what human permanence actually costs when nature refuses to hide the bill. On Earth, we inherit huge systems for free. On the moon, we would have to build those systems in miniature, keep them honest, and live inside the consequences when one of them drifts. The answer is difficult, but it is wonderfully concrete.